Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management. So within this module, we're trying to understand that how does the operating system manage the CPU by providing this abstraction of a process, right? And within the second module, currently we are on the fifth topic, that is time sharing. So as you know, within this topic, we are trying to understand that how does the operating system implement this concept of time sharing. So time sharing is basically when the operating system shares the CPU time among multiple processes so that we as users are able to run more number of programs on limited number of CPUs. So as we already discussed that this concept of time sharing is implemented via this technique called CPU scheduling, right? So CPU scheduling is basically a resource allocation technique where we are the operating system is allocating the resource which is the CPU among multiple processes, right? And we are trying to answer different questions related to CPU scheduling so that we are able to understand different aspects of it. So currently we are interested in the how question, and now after having discussed like in the previous videos that how can we transfer the control from the user process to the operating system, in this video finally we can talk about how we can switch from one process to another, that is via a context switch. So this is a very important concept in overall CPU scheduling. This is the mechanism via which one we can switch between different processes, right? So let's understand what is a context switch and how does it work in this video. So let us start the discussion with this slide. So as you can see, we are trying to answer different questions related to CPU scheduling so that we can understand different aspects about it, right? So we have already talked about the why question, and now we are interested in the how question. That is, how exactly is CPU scheduling done? What is the mechanism which makes it possible to switch different processes on the CPU? So that is the how question, the mechanism of CPU scheduling, right? So we have seen in the previous videos also that we have seen this diagram. So basically, what is this diagram trying to say? This is the CPU and this is the CPU time, right? And as you can see, we are time sharing the CPU. So basically, the operating system is time sharing the CPU among multiple processes. So you can see the time of CPU is being literally shared between different processes. So these boxes that you see, this is signifying that each process is running on the CPU for some time. So these are time slices which are occupied by different processes for executing instructions on the CPU. So this is basically time sharing happening. And when we are interested in understanding what is the mechanism behind CPU scheduling, we have to look at the part where we are switching between processes. So if we look closely at the point where we are switching between two processes, you can see something like this. There is some process, let's say process A, that is initially running on the CPU. Then there is a context switch where we are basically taking the control of the CPU from one process and assigning it to another. And after that, you can see some other process, let's say process B is running on the CPU. So although I have not shown here the time that is taken for context switch, but context switch takes some time, right? So although it is not shown, it is there, right? And now if you look closely at context switch, there are again multiple steps inside a context switch. So the first step, as we already talked about, is that the first step is to transfer the control from the currently running user process to the operating system, right? So as you can see, when the process A is running on the CPU, this means that the operating system is not running on the CPU, right? And unless the operating system is executing, it cannot do any kind of CPU schedule, right? So first of all, to do any kind of CPU scheduling to switch from one process to another, which only the operating system can do, first of all, we have to bring the operating system into the picture. We have to give the control of the CPU to the operating system. The first part is transferring control to the operating system. And in the previous two videos, we have talked about two different ways of doing this. One is that we can let the user process give up the control of the CPU on their own in a voluntarily manner, right? And the other way is that we can take away the control of the CPU from the process forcefully using a timer interrupt, right? So once the control of the CPU is with the operating system, there are two main steps. The first is that we have to select the operating system basically has to select a new process a different process to run on the CPU, right? So here we can see process A was running. So it could also happen that the scheduler inside the operating system, which makes these scheduling decisions, chooses the same process. It could also happen, right? So if there could be a timer interrupt, and let's say process A is interrupted, and instead of choosing some other process, it could very well happen that the scheduler makes the like selects the same process. Okay, but that is a different thing. The point is that a selection has to be made from all of the processes that are ready to run, and once that selection is done, we have to switch the control of the CPU from one process to another. This is the main part, that is switching to the next process. Till here we were executing before we were executing process A, then we entered the kernel, and now we are about to leave the kernel, so we will be handing over the control to some other process. So we have to make a switch. We'll see how this happens. This is the main part that we are interested in this video, like how exactly do you switch, right? You're executing from in the context of one process, and how do you switch to another process? This is the main part that we will try to answer in this video, right? And finally, when you have switched the process, you transfer the control from the kernel to the operating system. So when we switch, we are still inside the kernel. We are just in the context of another process. So we'll understand what I'm trying to say. We are initially executing the user process, then we enter the kernel, and then we switch the context. That is, within the kernel only, we start executing in the context of another process, and then we return the control back to the newly selected process. That you can see the last step is transferring control to user process. So this is the different actions, or you can say the different steps that happen inside this context switch. So we'll talk about the different steps in detail. So the next thing is that this is how overall, at a overall level, the same thing that I discussed can be described, right? So this is, you can say, process A, right? Process A was executing, and this flow diagram basically depicts the different steps that we just discussed. So process A is initially executing, and you can see we enter the kernel and do a context switch, and when we return, you can see a different process is executing. So we are switching from process A to process B. So these are the steps that happen, and now we are going to look at this flow in detail. So basically what we discussed here, the same thing is shown here in a different manner in the form of a flow diagram, right? So let's understand each of these steps and what is happening, so that we have a complete picture of the context switch. So we will be now after this video, you will have a complete picture of how exactly CPU scheduling is done. What is the mechanism behind it? We will be covering all the different pieces, right? So this flow diagram will describe all that. So let's study the different portions in this diagram. So now let us discuss the first step that is needed in a context switch, the entry part. So what do I mean when I say entry? So when I say entry, it means entering the kernel, right? So initially the user process is executing, and in order to switch from one user process to another, we'll have to do CPU scheduling, which will be done by the operating system. So the first step is to enter the kernel, or we can say transfer the control to the operating system. So we have already talked about this in the previous videos also. So let us understand with this flow diagram, right? You can see the blue region is where the user process is executing, and the red region is where the kernel is executing, right? So here we see that initially process A was executing, right? And after with that we did some things, and finally you can see in last step process B has started execution. That is a different process. So we have switched from one process to another. So what are all the different things that we did in between? The first thing is that we transferred the control of the CPU to the operating system. You can see we are entering the kernel, and the way to enter the kernel is via a trap, right? So what is a trap? We have talked about traps in previous topics also. So a trap is an event which, when happens, the control is immediately transferred to the operating system. So there are different events that cause traps. For examples, we have system calls, we have exceptions, and we have interrupts, right? Whenever we invoke a system call, we are requesting services from the operating system, right? So that control is transferred to the OS. Whenever there is an exception is basically some kind of error that the CPU encounters during execution, and when that happens, the CPU transfers the control to the OS to deal with the exception. And finally, An interrupt is a signal from a device that is basically requesting the attention of the OS. So in that situation also, the control is transferred to the OS. So all of these events are a type of trap, right? So as you can see, so we'll enter the kernel via a trap, and we have talked about this in the previous few videos also. That is, there are different ways to transfer control to the operating system. One is the cooperative approach, and the other is a non-cooperative approach, right? So both of these use traps, but the way is different, right? So in the cooperative approach, we are trusting the user process. We rely on the user process to give up the control of the CPU on a voluntary basis and give it to the operating system. We are expecting that the user process will either invoke a system call, or it could cause an exception, in which case the control will be given to the OS, or there could be some kind of device interrupt, right, which will transfer the control to the OS. This is the cooperative approach. We are relying on the user process to give up the control. But we also saw that there are several drawbacks to this approach, right? We cannot trust the user process to do things properly. There could be a bug in the user process. Let's say there could be an infinite loop, and when a process is inside an infinite loop, it won't be making a system call, it won't be causing an exception. And let's just assume that there is no device interrupt during that period. So we are stuck. The control of the CPU is stuck with the user process, and that is why relying on a cooperative approach is not useful, right? So the alternative to the cooperative approach is that we go for the non-cooperative approach. Here we do not rely on the user process. Here we have the mechanism to take the control of the CPU forcefully from the user process. Even if the user process is not giving it up on their own on a voluntary basis, we can take the control forcefully using a timer interrupt, right? We have talked about timer interrupt in the previous video. So a timer interrupt, basically, a timer is a device that has been programmed to raise an interrupt after every few milliseconds in a fixed interval, right? Whenever that fixed interval finishes, the timer raises an interrupt. So in a system with a timer interrupt, we have a guarantee that the control will eventually be given to the OS. So this is the difference between cooperative and non-cooperative approach. In both the cases, you can see, although the approach is different, the common thing is that the entry into the kernel will happen via a trap. Again, you can see in the cooperative approach, we are relying on system calls, exceptions, and interrupts. All of these are traps. And in the non-cooperative approach also, we are relying on a timer interrupt, which is again a trap. So the entry into the kernel will happen through a trap. And what happens when there is a trap? So the first thing that happens is that the registers of the user process will be saved, right? So first of all, before that, we'll switch from the user mode to the kernel mode, and the basically we'll jump to a trap handler. You can see after this part, when the trap happens, we start handling the trap. So the first thing that happens when a trap happens is that the privilege level is raised from user mode to kernel mode, and the execution starts from a fixed predefined point that is called a trap handler. The trap handler, its job, as you can see, as a name suggests, is to handle the trap. So the first thing it will do is that it will save the registers of the user process, right? We are kind of now pausing or halting the currently executing user process, and we would have to resume it at a later point in time, exactly from the point we are pausing it, right? Because the user process that we are halting, it is not yet done, it is not terminated. So it would have to be resumed at a later point in time. So the trap handler saves the state of the registers. Basically, at whatever state the execution was happening, all of those are saved, right? Once that happens, the trap handler determines the cause of the trap, like what is the reason why this trap happened. And depending on the reason of the trap, it invokes the appropriate trap handler. If it's a system call, then it will invoke a system call routine. If it's an exception, then it will invoke exception handler. Similarly, if it is an interrupt, then it will invoke the appropriate interrupt handler. So whatever it be the case, one thing to mention here is that if the interrupt is from the timer interrupt, then obviously we'll invoke the scheduler, right? But in other cases also, if the basically it's up to the operating system actually. In other cases also, after handling the system call or the exception or the interrupt, the operating system can decide to invoke the scheduler, and whenever it invokes the scheduler can make a context switch, right? So to make the scheduling decision or not, it's up to the OS. But the point is that since the OS has the control, right? Anyway, whatever be the reason, the control has been given to the operating system. It could be system call, exception, or interrupt. Whatever is the reason, once that trap has been handled, the operating system can very well invoke the scheduler and decide to switch the process, because we have to implement the time sharing, right? Everything that we are doing, right, all of this we are doing to ensure that we are able to allow multiple processes to execute on the CPU. We want to switch the control of the CPU among multiple processes. So if the operating system has the control, then it can very well decide to do the scheduling. So this was how we enter the kernel and what are the things that we do before making the actual switch. We have not talked about actual switch, right? We have just talked about how can we enter, what are the different mechanisms by which we can enter, and what are the steps that the OS takes once the entry is done. So now, once the entry is done, let's talk about the core part, the main part, that is the actual switch, the actual context switch, where we are switching from one process to another, right? Let's talk about how that happens. That is the switching between processes. So once we are once we have entered the kernel, right, the next part is to actually switch the process. So let's see how that happens, right? We are now interested in this fourth step. So after you have transferred the control to kernel, there are two important steps. The first is that the scheduler that will perform the CPU scheduling, right, that has to select the next process. So for example, if here process A was running, then which process should run next? So first of all, that decision has to be made, right, before actually making the switch from process A to some different process. That different process has to be selected, and that will be done based on some algorithm. As you can see, the scheduler selects the next process to run on the CPU based on some algorithm, right? And this algorithm is called the scheduling policy, right? So we'll spend a whole amount of time understanding what is the scheduling policy, what are different types of algorithms that exist out there, which help the scheduler to make this decision in the next topic, right? So for now, at a very high level, you can understand this in this way, is that there are different goals for a computer system, like optimizing for throughput or optimizing for response time. So depending on what is the goal of the system, the scheduler has to make the correct appropriate decision, and it can be this decision can be complex. So there are certain algorithms that help the scheduler to make this decision. So with this algorithms or scheduling policies, we'll talk about them in the next topic. So for now, okay, there is some way we can think of this in this way, is that there is in some way the scheduler makes the decision. So once the selection is done, what is next? Once the scheduler has selected the next process, the actual switch will happen, right? The actual switching between the process will happen. So this is the important part. So how does this switch happens? A process switch essentially involves saving registers of the current process and restoring registers of another process, right? So whichever process was executing, for that we had to save the registers, and we have to restore the registers for the next process that we have selected, right? So in this case, process registers for process A will be saved, and registers for process B will be restored, and that is how there is a context switch, right? So let's see how this is done. So to understand this, let me give you an analogy, right? Let's say you are reading two books, right? And the way we read books is that generally we read them in a sequence, right? And to mark where we had like last read, what is the last page that we had read, we use bookmarks, right? So we'll understand how, when we are reading books, and how the concept of bookmarks is similar to what we do when we are switching between processes. So let's say you have two books, and you are starting from page 0, you're starting from the first page, right? And so let's say you select this book, the red book, to read first, and then you're reading this book, and let's say you read 50 pages, right? And after you're done with 50 pages, you decide that now you want to read the blue book, the other book. So what do? You first of all put a bookmark at page number 50, so that when you like later on resume reading this red book, you know where exactly you had left off, right? So this is the concept of a bookmark. It allows you to remember where you had last stopped reading, right? So after this, you switch to the blue book, right? And again, you're starting this book to from the first page. So let's say you read this book sequentially, and you read till page number 70, right? So just like for book 1, the red book, now you want to, let's say, switch from book 2 to book 1, from the blue book to the red book. So what do you do? Again, you put a bookmark at page number 70, so that when you resume book 2, you can resume from page number 70 where exactly you had left off, right? You're getting the idea what we are trying to do here. So now let's say you want to read this book 1 again. So you will resume exactly from page number 50, because, and it will be easy to do so because you had already bookmarked the page. So you resume this first book and start reading from page number 50. You read for some time, let's say you read 100 pages and go till page number 150, and again you can switch to another the other book, that is book 2, right? The same thing you have to repeat. You just bookmark at page number 150, because at a later point in time you might want to come back and resume. So you switch to book 2 and let's say you read till page number 120, right? So this is the example that will help you to understand how we exactly switch between processes and why we are saving the registers. So now let's come back to processes. So this was about books. So when you're reading books, you read them in a sequential manner. You read one page after another, and there could be case that you're reading multiple books. And to remember, so in order to read multiple books, it might be the case that you might not read each book at one go, and you might be switching between different books. So in that case, when you're switching between different books, it is a good idea that you use bookmarks, so that when you're switching from one book to another, you can like save like at which point you are reading that particular book that you're about to leave, so that when you resume that reading that book at a later point in time, that bookmark will be useful. So this is about books. Let's come back to processes. So in case of processes, we know that all of the information that is required to represent a process is stored in a process control block, right? So the process control block is like a data structure, which is generally a C style structure, which stores all of the information that is necessary to represent a process. We have talked about process control blocks, and as you know, this is the process control block for XV6 operating system, right? So we have been using this as an example throughout this course. So if you see this process control block, there is a structure context, right? What is this context? This is a field which acts like a bookmark for processes, right? So this is how it looks like. If you see saved registers for kernel context switches, right? So you can see the context is a structure which basically contains a bunch of registers, right? For example, there is this stack pointer and there are many temporary registers. So what is, so basically the context is basically a set of registers. The set of registers is saved in the context of the process control block. It is like a bookmark for process execution. So now we are going to see how we are going to switch between processes, and it will follow the same analogy that we saw in the case of books. So when you're executing processes, right, you execute them in sequence, right? Each instruction is executed in sequence, and as we discussed, we are not going to execute each process in one go. We are going to switch between different processes. So when you're pausing a process, you have to save exactly where you had stopped that process. So that is where context comes into the picture. Context helps us out by saving the state of the CPU registers when a current process is executing. So what happens is that when a particular process is executing on the CPU, the register values keep changing, right? As the execution proceeds, the register values keep changing, and these register values build up a state. At any given instant, the values of the registers like reflect the kind of computation that is being done by the process. So if at any point in time you halt or you pause that process, those registers have to be saved, right? These set of registers together together make up the context, and you can think of the context as like a bookmark, right? So let's see the example of the processes. So let's say you have a CPU, right? And currently this process A is running on the CPU, right? And this is the operating system, and this is the process control block for process A. So currently the operating system is pointing to this. When we say pointing to this, it means that the operating system has selected this process A, for which this is the process control block. So operating system is like using this process control block to signify that this is the process control block of the process which is running on the CPU, right? So as you can see, this is process A, and as it executes, this is the registers of the CPU whose values will keep changing. So this is what is important. As process A is executing, the contents of these registers that are inside the CPU, the temporary registers, keep changing, right? So this was process A. Now let's assume that there is another process in the system, which is process B. And this is the process control block for process B, right? And this is the context for process B. Let's assume that process B was executing earlier also, right? And it had been paused. And when it had been paused, this was the snapshot of registers. As you can see, this is the snapshot of registers, and this is the context that is stored in process B. So now let's assume that the operating system decides that uh, it wants to give the CPU to process B, that is make a context switch from process A to process B. So let's see what happens. So the first thing, it will deallocate the CPU from process A. We have entered the kernel, and the control of the CPU is now with the operating system. So what happened here? So if you see, this is process A, and these are the registers. So when you switch out a process, when you are about to switch to a different process, you first have to save these registers in the process control block, right? So when process A is being removed from the CPU, the snapshot of registers is taken and it is kept in the context field of the process control block. So now when process A will be resumed at a later point in time, we can use these registers, right? So process A has been switched out of the CPU. Now we have to bring the process B into the onto the CPU. So the way we will do is that we'll load the context, that is, load the set of registers, the snapshot of registers that was uh, when the process B had been switched out, right? So we are assuming that process B was running previously, and this was the state of registers where we had left process B. So we load that in and resume executing from the same point. So it is like a bookmark. So when you have to like switch from one book to another, you insert the bookmark into the first book, right, where you are kind of saving like the last page that you're reading. And when you start reading when you resume reading the other book, you use the bookmark to resume from a fixed point, right? So this is how context and bookmark are similar. You can see when we are switching out a process, we are taking a snapshot and saving the context in the process control block. And when we are bringing another process, we are loading the context in the CPU to start execution from the point where we had left that process. And as you can see, operating system is now pointing to process control block of this process B to signify that this is the process which is currently executing on the CPU. Let's say process B, let's say now operating system decides to switch from process B to process A. The same steps will be followed. Process B will be taken out and will take a snapshot again and save the snapshot in the process control block of process B. And now when we are about to resume process A, when we are switching from process B back to process A, we'll load the context, we'll load these registers into the CPU and start resuming exactly from the point where we had left off. So this is the way switching between processes happen. The main part, the crucial part in the switch is the saving of registers and loading of new registers. So the switching of registers is what makes the context switch happen, right? So now let's come back to this flow diagram, right? So we have talked about this fourth step in detail right now, right? That is where the actual switching of processes is happening via this switching of registers. We save the registers of one process in its context, which resides in the PCB, and then we load the registers which are in the context of another PCB into the CPU, and that is how the actual switching between processes happens, right? So one important point that I want to bring to notice here is that after switching registers, it appears that the trap had occurred from process B and now we are returning. So what does this mean? So this is a very subtle point that I want to make. So let's talk about the case when there is no context switch, and let's just assume that we are entering the kernel from process A and leaving it like returning back to process A only, right? So when that is the case, the thing is that we are entering the kernel through some process and then we are going back to the same process. In the case of context switch, what happens is that you enter the kernel from process A, let's say in this case, and here is somewhere you make a switch and you return to a different process. So you're entering from a different process and you're returning to a different process. So just before the switch, you are executing as if you are processing the trap from process A, right? Like handling the trap from process A. And just after the switch, it appears that you are handling the trap from process B, right? So this is what I'm trying to say. You enter the kernel in the context of one process and you leave the kernel in the context of another. So just before the switch, it appears that we are executing that trap from process A, and just after the switching of registers, it appears that we are handling the trap from process B, as if we had entered the kernel like via a trap from process B only, right? And now once the trap is handled, we will return to process B. So this is how context switch is different from a normal trap. In a normal trap, when we're not switching, we enter the kernel from one process and we return back to the same. In the case of a context switch, we enter the kernel via one process and leave the kernel uh, and return to some other process, right? So this was about switching of processes, right? So we have talked about entering the kernel. We have also talked about how we actually switch between processes. Let's talk about the last remaining part, that is leaving the kernel, which we call as exit. So now if you look at this flow diagram, we are done with these 4 steps, and now steps 5, 6, and 7 remain. So once we have switched to a different process, in this case process B, what is remaining? The remaining thing is to return from the trap. So the way this is done is that we prepare for return, we restore the registers of process B, right? And then we execute the return from trap instruction. When that happens, the privilege level is dropped from the kernel mode to the user mode, and we resume executing the instructions of process B from the point we had left off, right? So this is how we leave the kernel. So this is the part that I'm talking about. If you see this context switch, there are 4 major steps. First is transferring control to the OS, which is the entry part. Then selection of the next process using some policy or algorithm, which we will cover in the next topic. Then there is the switching to next process, where we switch the registers. That is what we discussed in this video. And then there is the transferring of control back to the user process, right? Which is the exit part. So there is something that we left, we did not discuss. You might have noticed, if you had been paying attention, that I talked about 2 different kinds of register saves and restores. That is, when we were entering the kernel, there also I said that we are saving the registers, and during the context switch also I said we are saving the registers and restoring them, and while leaving the kernel also I said we are restoring the registers. So I'm talking about 2 savings and 2 restores. So what is the difference between these 2 saves and restores? So the point is, there are 2 pairs of saves and restores. One pair I have shown in red color, the other I have shown in blue color. So what are these 2 pairs of saves and restores, and how they are different? So the one pair is that when you are entering that kernel via the trap, and when you are leaving, there is one save and restore while entering and leaving, and there is one more save and restore during the actual context switch. So what is the difference between them? The difference is that when you are entering the kernel, you are saving the uh, user registers from the user space. Basically, the registers at this point, when you are executing at this point, you are executing the code of the user process, right? This blue arrow, if you see here, you are executing the instructions of the user process. So when you are saving the registers when entering a trap, these registers reflect the state of execution of the user code, right? And let's just assume that there is no context switch. Even then you have to do this, right? And the same thing when you're leaving the kernel, the registers that you're restoring, these are for the user code, right? These are not for the kernel code. So at this point you are executing user code, and at this point you will resume executing user code. So these saves and restores are for the execution of the user code. But and these are always required whether you do a context switch or not. If you're entering the kernel, and and once you're leaving the kernel, these pair of saves and restores will always happen. That is, registers of the user code you'll always have to save when entering the kernel. So that is the blue, that is the save and restore that's shown in blue color. You are saving user registers for process A, and you're restoring user registers for process B. This save and restore will always happen irrespective of the fact that you do a context switch or not. It could be a simple system call and then you leave, but you'll always have to do this. But coming to context switches, you see, once you're context switching, you have executed kernel code for a fair amount of time, right? You came in here, you saved the user registers, now you started executing kernel. The kernel will be handling the trap, it will be detecting the reason of the trap, invoking the correct trap handler, selecting the next process. So you see, we have executed fair amount of kernel code here, right? When we have entered the kernel from process A, after this point we have already saved the user code registers, but after this we are executing kernel code, and now when we are making a switch, we have to save the kernel registers also, right? So when we make a context switch, we are actually switching between kernel registers, the registers that you save in the context of the process control block. Those are basically the state of kernel registers. When you're making the switch, it is a snapshot of kernel registers. So that is why we have two different pairs of saves and restores. So here we are saving the we are taking the snapshot of execution of the user code. The registers here are reflecting the user code execution, but after here, from this point onwards, we are executing the kernel code, right? So this part is executing the kernel from the perspective of process A. You can think of this in this way, that before the switch we are executing the kernel from the perspective of process A. After the switch we are executing the kernel code from the perspective of process B. So at this point when we make the switch, these are the kernel registers. So this is a different switch from the this is a different save and restore, right? So the first kind of, so let me summarize. In case of a normal, whenever there is a trap, you'll have to save user registers while entering and restore user registers while leaving, and these registers are actually a snapshot of the user code execution, right? If you do a context switch, then there is another kind of save and restore, that is for the kernel registers, right? So we have, in this case, the red color that you see, this pair of save and restore is where we are saving kernel registers and then restoring kernel registers. So these are the two different kinds of saves and restores that happen. This red one will only happen if you have a context switch. This blue one will always happen if you enter the kernel and leave the kernel, right? So this was about this was one detail, and this is how the overall context switch looks like. You enter the kernel, then you make the switch between, you select the different process, you make the switch, and when I say switch, this is the kernel register switch, and finally you leave the kernel to some different process, right? So this is how we actually do a context switch from one process to another. The final point is that context switches can be expensive, right? You are doing a lot of things. There is a trap, you handle the trap, you switch the registers, then you return from trap. So and this is pure overhead. The point is that you're not doing any kind of useful work when doing a context switch, right? So the computations, the instructions that happen during a context switch, they are not useful at all, right? So they are pure overhead. So when I say they are not useful, obviously they serve a purpose, but they are not serving the purpose of the user, right? So they are overhead, and so the operating system should avoid too many context switches because they can be expensive. Switching from one process to another also has this delay, because one process builds up the state and suddenly you switch to another process. So different parts of the system, the memory, all of these build state, which kind of, when you change, there is a delay. So context switch is expensive and it is pure overhead. So the operating system should limit the number of context switches. Obviously, it should not be the case that there are too few context switches. Too few context switches will mean that we are not sharing the CPU time properly. The system will become not so responsive. But on the other extreme, if you're doing too many context switches, then we are spending time on doing something that does not really is useful to the user. It is overhead. So there should be a fine balance on the number of context switches that the operating system should perform, right? So guys, this was it for this video. So now we have completely understood the mechanism of how the CPU scheduling is done, right? The 4 questions that we wanted to answer, of all of them, the how part has been answered. That is, what is the mechanism which allows you to switch from one process to another, right? We covered about different steps here, except for how we select, except for this box, that is selecting the next process. This we will cover in detail when we talk about scheduling policies in the next topic. But apart from this, we talked in detail how you transfer the control using cooperative, non-cooperative approach, how you switch the registers, how you actually switch the process, and how you transfer the control back to the user process, right? So this, all of these together make up the context switch, and now we know that what is the mechanism which makes it possible to switch from one process to another in a computer system. So guys, this was it for this video. Thank you very much for watching. I'll see you in the next video. Thank you.